In this class, we are going to solve a magnetic circuit problem. This is a university question, and in this class, we are going to solve this problem. And the problem, the examiner given this problem, the statement of the problem is an iron ring of cross-sectional area 6 centimeter square. So given the magnetic circuit like this, that is an iron ring of cross-sectional area 6 centimeter square. So cross-sectional area A equal to 6 cm square, that is equal to 6 into 10 power minus 4 m square, that is meter square, and is wound with a wire of 100 turns like this as shown in this figure. So number of turns of the coil is capital N, that's equal to 100, and the ring has a saw cut of 2 mm shown below. Calculate the magnetizing current required to produce a flux of 0.1 millivapor. Flux phi is equal to 0.1 millivapor. So if mean length of magnetic path is 30 centimeter, mean length L is equal to 30 cm, that's equal to 30 into 10 power minus 2 meter. Relative permeability is given of iron is denoted by mu r is equal to 470 Henry per meter. Neglect magnetic leakages and fringing. So in almost all the problems, you have to assume that magnetic leakages and fringing are absent. Magnetic leakages means now we are going to draw the ring like this. And turn number of turns 10, number of turns. Okay, actually it is 1 2 3 number of turns, but as just imagine that it is n equal to 10. Sorry, n equal to 100, not 10. Sorry, and we have is this magnetic leakages and fringes. Magnetic leakage means if I is flowing then what you will get a magnetomotive force mmf is generated, will be produced, and with the uh, due to the magnetomotive force we will get we will get the cause, that is magnetic flux. So magnetic flux will be like this, magnetic flux in a closed path like this. Okay, so there will be a lot of number of magnetic lines. Okay, now the magnetic lines of force will be like this. Okay, they will never intersect each other, and are confined to, not only confined to the this ring actually, but also the magnetic lines of force will complete its closed loop like this also, this manner also, and in this manner also, like this also. Okay, in this manner also, like this also. That means in this path, small path, some of the flux lines will complete its path like this also. Okay, and this, if you observe these flux lines does not pass through this the entire uh, path which is in our discussion, and this flux links with only with this coils, number of turns, 100 number of turns, that is. So this kind of flux lines are known as leakage fluxes. Leakage fluxes, that is flux, amount of flux that links only with the coils. Such fluxes are known as leakage fluxes. And the fringing means actually when a change of medium is there for the flow of flux lines. So we are assuming that it is the flux lines of force are directing in this manner parallelly, right? But actually, if this depends upon the amount of flux. Why? Because if you increase the amount of flux, the number of flux lines also increases. Number of flux lines passing through a given cross-sectional area also increases. That means the flux density also increases. So if the flux density increases, that means for a particular given cross-sectional area, a large number of flux lines are flowing. That means the reluctance will be increased, so that sum of the flux lines uh, will be traveling in this manner, like a curved manner, like this. Okay, like this. So what the examiner is telling to you is that you neglect these two effects, that is leakage flux and fringing. This is known as fringing. So you neglect these two effects, so that you have to consider the flux phi is confined to this path only. Okay, so that is our assumption for problem solving. Not only in this problem, but in all the magnetic circuits that we will discuss, will be having by default these two assumptions. Okay, now what? Now you have to calculate. Yes, the examiner is asking you to calculate the magnetizing current required to produce a flux of 0.1 milliweber. That means okay. Yes, that means he or she is asking you to find out this current I, this I, current I flowing through this coil of number of turns equal to 100. So how to model this? How to model this for this? So this circuit, in this circuit, actually this is a series, is an example for series composite magnetic circuit, in which iron magnetic material is there, and that is in series with some air, okay, air gap. So the with respect to the the traveling of magnetic flux lines, these two medium are in series. That means the flux lines will first travel through this iron, okay, and then it is not getting divided. The flux lines are not getting divided. The same flux phi is traveling from iron to the next medium air. The same amount of flux phi. So that means in a series circuit, you have, in a series electrical circuit, you have, if you consider these R1 and R2 resistance, then you can observe that the current I is same in R1 and R2. That means this may be some other some material, and this may be another material. So and these two are having two different properties of resistive properties, having R1 and R2 magnitudes. So in this, if it is connected in series, means the current I is constant. Current I will be flowing through in the two different materials. In the same manner, analogous quantity of I is flux of phi, right? And we have two materials connected. Then that means if the phi is constant, just like I, phi is constant in the two medium, okay, in the two uh, medium, okay, the two medium, that then this type of magnetic circuit is known as series magnetic circuit, like your series connection of the resistances. Okay, so our conclusion is this is a series magnetic circuit. Conclusion, a series magnetic circuit. So the first step is first you identify whether the magnetic circuit is a series magnetic circuit or a parallel magnetic circuit. That means whether the flux phi is dividing into phi 1 and phi 2, or flux phi is constant throughout the path. okay, that you need to identify. So in this case, this is a series magnetic circuit, so we will model like this. This is magnetomotive force, and here we have, yes, uh, yes, reluctance S1 and reluctance S2, and also we have yes, like this, in this manner. Okay, that means this S1 is S1 equal to the reluctance of iron. Okay, S2 is the reluctance offered by air. Okay, so the reluctances are I have represented like a box. Okay, that's all. And we have flux phi like this one like this. So in order to find out the magnetizing current I have to find out magnetomotive force mmf. I will find out, and we know that mmf is equal to ampere turns, that is equal to Ni. So if you get this mmf, then you will divide the mmf by your number of turns 100, then you will get the magnetizing current I. Okay, current I. So that is what our procedure. For that, the examiner has given the phi 0.1 milliweber. Okay, then the examiner again given some dimensions of the iron and as well as the air. Okay, air column, air core, as well as the iron core, right? So now the cross-sectional area, yes, and also he has given the yes, is found the mean length of magnetic path is 30 centimeter he has given. So our objective is to find out S1, sorry, to find out S1 and S2. So S1 will be equal to L divided by, applying the formula, L divided by mu 0 mu r A. So in this case, L will be, S1 is the reluctance offered by the iron, so it will be, L will be the length of the iron core. Okay, that is L1. L1 equal to mean length, mean path length of iron core. Okay, that is equal to, yes, that means mean length means I'm drawing a, what you call a circle. Okay, a circle exactly in the middle of this, sorry, okay, okay, this is my, this is my ring, okay, this is my ring. So this is, I'm drawing a circle. Okay, circle exactly at the center, and this is given as the mean length. Okay, mean length mean length of the magnetic path is 30 centimeter. He has given. So this is L mean length equal to 30 cm equal to 30 into 10 power minus 2 meter. Okay, so L1 will be the mean path length of the iron core only. Okay, because this 30 centimeter includes both the iron core as well as the air core. So you have to subtract this air core length. Okay, that means 30 centimeter minus what? Your 2 mm. 2 into 10 power minus 3, that is equal to 30 into 10 power minus 2 minus 2 into 10 power minus 3. Okay, that means 300 minus 2 into 10 power minus 3. So L1 will be equal to 298 into 10 power minus 3 meter. Okay, that means that's equal to 0.298 meter. This is L1. Now we have L2. That means okay. So what we will do? What we will do is we will calculate. In the next step, we will calculate this S1 equal to L1 divided by mu 0 mu r into A. So that will be equal to 0.298 divided by 4 pi into 10 power minus 7. Mu r is given 470 into A. A is also given. A is cross-sectional area, and that is given as 6 centimeter square. So we will have 6 into 10 power minus 4 meter square. So S1 will be equal to let me calculate the let me do the maths first of all. Okay, 0.298 divided by okay, you got the answer as 841351.58. So this is the magnitude. Then what is the unit of reluctance? Actually, the unit of resistance in an electrical circuit is ohm, but the unit of reluctance in a magnetic circuit is Henry inverse, H inverse. Okay, this is the unit. So in examination, you should write both the magnitude, not only the magnitude but also the unit you should write. Okay, that is important. Then S1 is we have calculated. Then next S2 is equal to L2 divided by mu 0 mu r into A again, and that's equal to L2 is 2 mm2 into 10 power minus 3 divided by the same mu 0 mu r is 1, so 4 pi into 10 power minus 7 into 6 into 10 power minus 4. Okay, so we will get S2 is equal to, we got, let me calculate it. Okay, so we got the answer S2 equal to this much. Okay, S1 we got. So we will next we will going to apply the KVL as well as Ohm's law. KVL in a magnetic circuit and Ohm's law. Okay, or Ohm's law and KVL. So that means we have MMF, required MMF will be equal to, if you apply KVL or KVL for this magnetic circuit, so MMF, this is plus minus, this is plus minus, this is plus minus, so MMF will be plus and minus, let me say this is MMF 1 and this is MMF 2, so plus to minus minus, so MMF 1 minus MMF 2. That means MMF equal to, or 80 MMF, or otherwise you will call it as ampere turns. So 80 will be equal to 81 plus 82 instead of MMF 1 and MMF 2. Okay, so and this 81 will be equal to 5 into S1 and 82 will be equal to the same 5 into S2. So again we have 5 into S1 and 5 into S2, that is 81 equal to 5 means 0.1, I think. Okay, previous 5 is given as 5 okay 5.1 millivapor, so into 0.1 it's okay, it's already 81 equal to 5, 0.1 into 10 power minus 3 Weber into 5 okay, 5 into S1, we have S1 is this much. Okay, so that means here we have 10 power minus 4 actually. So 10 power minus 4 into this number, you will get 1, 2, 3, 4, 84, 84.13. So 81 will be 84.13 ampere turns, 80 or ampere simply, and 82 will be 10 power minus 4 into this. That means 1, 2, 3, 4, 265.4 265.4 ampere turns, and both so total MMF for total ampere turns will be addition. So you add, what you will get is Okay, 349.53 ampere turns. So, and that will be equal to your N into I. So, your answer, the examiner is asked you to find out the magnetizing current, that is I here. So, I will be equal to 349.53 divided by N, that will be equal to 349.53 divided by 100. So that will be equal to, so the answer will be I is equal to 3.4953, which is approximately equal to 3.5 ampere. So this is your answer. So in this way you should solve the problem. Now this is your an example for the series magnetic circuit actually. Like yes. So we have discussed the previous problem, right? The thing is, you can also solve this problem by another different method. So before discussing that method, you should know that you should derive a formula. That formula is we have ampere turns AT, or ampere turns is also known as mmf, a magnetomotive, which is the analogous quantity of voltage in electrical circuit. So yes, this mmf by Ohm's law in magnetic circuit, we have phi into reluctance, phi into S, phi S. But phi, and I'm deriving an equation for ampere turns or mmf, or voltage drop, mmf drop, you can say mmf drop in a magnetic circuit. I'm deriving the formula for the magnetomotive force drop, mmf drop in a magnetic circuit in terms of H and length L. H is nothing but your magnetizing force, okay, or magnetic field intensity. So I will substitute this phi with, we know that phi is magnetic flux. But if we have B, that is magnetic flux density, then you can find out the magnetic flux, that is B into A is magnetic flux, right? Why? Because magnetic flux density B is phi by A, so B into A is phi. So B into A into S is our equation becomes. Now we have B, I'm going to substitute for B. We have already learned that B is equal to mu 0 mu r h, or B is equal to mu m h. So I am substituting this for B, that is mu m into h into A into S. So that will be equal to, that is LHS side, we have again we have mmf drop or ampere turns. So this mmf will be equal to mu m h into A. Then I am going to substitute for the reluctance formula. We have S, reluctance S is equal to L divided by mu m A. That is mu 0 mu r into A. Actually but mu m is the formula. So what we will get, mu m got cancelled, a got cancelled, and finally we have mmf, magnetomotive force drop, equal to h into L. That means if we know the magnetic field intensity, okay, if we know the magnetic field intensity, yes, this was our structure, right? So if that means if you know the magnetic field intensity H in this air gap, that is, let us say, let us denote as H air. So if you know that, and if you know the length of that air gap, then the mmf drop or the ampere turns 81 will be equal to, or 81, not 81, 82 will be equal to just H air into L. Okay, so that means yes, you have if you have H, yes, instead of applying, yes, you should apply this KVL or KML, Kirchhoff's mmf law, for this circuit. Or so if when you are applying KML, then what we have written is mmf total magnetomotive force or ampere turns will be equal to 81 plus 82, right? 80 total 80 equal to 81 plus 82. This 81 is the ampere turns or mmf volt drop in the iron part, and 82 that in the air part. Yes, that is what 81 and 82. So in order to find out this 81 and 82, what we have done is we have calculated the reluctances S1 and S2, and we multiplied with 5 into S. But we have proved that in the previously we have proved that AT is equal to 5 into S. 5 into S can be reduced to H into L, this formula, right? H into L. So 5 into S1 will be equal to H into L1, and 5 into S2, because it is a series magnetic circuit, 5 will be constant, flux will be constant for both the material. So 5 into S2 can be can be replaced by H into L2, right? So that means if you find out H, you find out H. That means H is, yes, this phi is given as 0.1 milliweber, 0.1 milliweber. Okay, so you find out H from that. H will be equal to H. Actually, first you find out B. Okay, flux density B. So that will be equal to phi by A. That means 0.1 to 10 power minus 3 divided by A, 6 into 10 power minus 4. That much Tesla. Okay, now what you have to calculate is B we got. Okay, some I think it is 10. So 1 by 6 you will get 1 by 6. That means 0.167. Okay, H. That means that much ampere. H means magnetic field intensity, that is Ni by L. Okay, that means ampere turns per meter. You got this. H. This is for iron. Now the mmf drop. If you want to find out the mmf drop in this iron part, then what you have to do is you multiply this H iron simply by the length of iron core, L iron. Okay, that means 0.167 into length, right? Okay. Okay, actually this is B. We have calculated B. Sorry. Yes, B. We have calculated B. B is equal to 1 by 6. That is B. Okay, B will be equal to 1 by 6. That means B is equal to 0.167 Tesla. So B we have got. Now you have to find out H ion. So H ion, how to find out is H ion we have the relation B is equal to mu 0 mu m H, right? So H will be equal to B divided by mu 0 mu r. That means mu m. That means, okay, so H ion will be 0.167 divided by this mu m, that is mu 0 mu r, that is 4 pi into 10 power minus 7 into mu r means relative permeability of the iron, that is given as 470. So you will get H iron, right? Now you do what? H iron into the length. Length means here the length is given as length we have calculated. Okay, we have calculated, I think, L1 mean path length of the iron core. That is L1 equal to 30, right? Yes, 30 minus this is okay. That means 0.298 meter. So you multiply this HIN into this 0.298, then you will get 81 or mmf1. Okay, similarly you find out the 82 also. 82 will be equal to H air, you have to calculate, into air gap length L2. Okay, right. Now in order to find out H air, what you have to do is H air is found out by the same formula, because we have B, again B is equal to 5 by A again. Phi is given as 0.1 into 10 power minus 3 and A is also given. The same area of cross section can be applied to the air core also. So it will be 6 into 10 power minus 4, I think. Yes, so B will be constant, 0.167 Tesla or Weber per meter square. Now what is changing is have B by mu 0 mu r equal to H air. That means this mu 0 is 4 pi into 10 power minus 7 and mu r is the permeability of the relative permeability of the air, that is nothing but 1. Okay, so in that way H air will be different, and H air will be H air into the air gap length at L2, we will, if you multiply these two quantities, then you will get 82. Then again 81 plus 82 will be the total ambient 80. So in that manner, you can find out the current also, because 80 divided by the number of turns you will get, then you will get the magnetizing current. Okay, so these are the two methods. Okay, so either of the method you can follow in the exam. Okay, now again I'm considering the next taking the next question. Okay, there is nothing but question. Yes, this. Anyway, okay, not this question. Yes, this question. Okay, this is our question. Let me. Yes, figure 612. Figure 612, and this figure. We have this figure. Sorry. This figure we have. Yes. Let me draw this figure, and that's okay. Now, as figure 612. Okay, you refer this figure 612. So the problem is the magnetic circuit shown in figure 612 has following dimensions. It is having a length L1. L1 length is given as 10 centimeter. Okay, and L2 equal to L3 equal to 18 centimeter. That means yes, I have a figure like this. Yes, and small air gap, and then I have okay. This is my structure looks like. Okay, actually, yes, this is something like a bigger. Okay, and yes, like this. Okay, and I have a winding placed on this limb, the top limb, like this. Okay, yes. And I have current flowing through this winding I, and I have the in the problem the problem it is given that L1 equal to 10 centimeter, L2 equal to L3 equal to 18 centimeter. That is L1 is nothing but okay, L1 is this length, L1 this length. Okay, this is L1. Length is L1. Okay, this length is L1 up to here, and L2 and L3 are equal, and L2 and L3 are given as from this point, from this blue line. Yes, this blue line. Okay, this is L2. Similarly, sorry, this is, I think it is L3. Okay, this is L3, L3, and L2 is yes up to this length. This length actually it is mean length. Okay, mean length of the core. This is L2. This is L2. So L2 it is given as L2 equal to L3 equal to some value, and L1 is given as 10 centimeter I think, and L2 18. Okay, 18 centimeter. And the cross-sectional area of L1 path is given as 6.25 centimeter square. As the cross-sectional area means here. L1 section means here. This cross-sectional area is given as 6.25 centimeter square. And the cross-sectional area of L2 and L3 paths are both are same, are equal, that is 3 centimeter square, 3 centimeter square each, 3 centimeter square each. Okay, that means this cross-sectional area and this cross-sectional area, and these two cross-sectional areas are equal, and it is equal to 3 centimeter square. Actually it is not equal in the figure, but it is equal. There given that they are equal, L2 and L3 paths are equal, and length of air gap is equal to 2 mm. This air gap is here, situated here, and this is 2 mm air gap. Taking the relative permeability of the core material as 800, as core material relative permeability, it is given taken as mu r is equal to 800, and air relative permeability of air is nothing but 1. We know that. Find the required current in 600 turn exciting coil. That means this winding is having a total number of turns equal to 600. That coil is having 600 turns. Okay. And the examiner is asking you to find the required current, that is magnetizing current. Magnetizing current in that 600 turn exciting coil, so as to establish a flux of 100 microweber in the air gap. Neglect leakage and fringing. So that is what our problem. So in this problem we have the magnetic circuit model like this. Yes, the winding, and yes, this current will produce an MMF, a total ampere turns 80, and that will drive a flux flux, and this flux will be taken as phi here, phi inside this coil phi, and when it is reached here, this there are two limbs, this right limb and left limb, and these two limbs actually they are of the same dimensions, same dimension. So S1, S2, and S2 is the reluctance offered by this left limb, and S3 is the reluctance offered by the right limb. So S2 will be equal to L by mu m A, where L is L2 and A is the same cross-sectional area. So mu m is also same. So S2 will be equal to S3, and that will be equal to the L2 divided by mu m A. Sorry, yes, L3 and L2. So the reluctance offered by these two paths will be are same. That means it is like your electric circuit in which the resistance offered by the two paths are same. So the current will be equally distributed in that two paths. So similarly, you will get phi by 2 here and phi by 2. That means half of the flux is flowing and completing its closed path in this right limb and then left limb. Okay, half will be going in the rightward limb, and then the remaining half will be flowing in the left half limb. Okay, so yes, and then we have another value of reluctance offered by this main limb. Okay, the central limb actually. Okay, that is some S1, you can say, and this is I'm denoting as S2. Okay, and this limb offers S3 reluctance, and this air offers a reluctance SIR. Okay, and okay, then we have this air. Actually, this air gap is present at the center. Okay, not at the center. Actually, it is having at the bottom portion, and this reluctance, the reluctance offered by the bottom portion of the central limb can be neglected. Okay, it is neglected actually. So it can be neglected, or yes, it can be neglected, or you can have that. You can take that reluctance also. That is, let me take it as S1 dash. Okay, but the circuit becomes very complicated actually. Okay, you can take it. Okay, so we will consider all the reluctance. So the magnetic circuit model will looks like this. We have the MMF. Okay, and we have the S1 here, S1, then we have okay S2 here and S3, I guess, right? S3 we have, and here we have S air, and again we have S. Okay, we have S1 dash. Okay, this is our magnetic circuit. Okay, so S2 S3, that means here it is S2 and here it is S3. So this is our magnetic circuit model. Okay, now what is the question? Question, you have to find out the required magnetizing current, the same magnetizing current. So you yes, then you find out this S1. The step I will explain only the steps. You should find out the answer. First, you find out this S1, and that will be equal to L by mu ma. So L will be L1. L will be L1, and this L1 L1 we have, and this L1 actually L1 minus 2 mm. L1 minus 2 mm is your L here. Okay, L. That means this S1 actually, this I'm combining this S1 plus S1 dash, that's equal to S. I'm taking. So S will be equal to L by mu ma, and this L will be equal to L1 minus 2 mm. 2 mm. So you calculate this, then you will get L, and substitute here L by mu ma, where mu m is mu 0 mu r, that is mu 0 is 4 pi into 10 power minus 7, and mu r is given as 800. Okay, then yes, S is find out. So you will get, you can add these S1 and S1 dash, and you can have S. Then we have to find out this S air. S air you have to find out. Okay, S air will be equal to again L air divided by mu 0 mu r into A. So you will get S air value also. Okay, S air value you got, S you got, then calculate S2 and S3. Okay, because A is given, so you can calculate it. Then you got all these reluctance, different reluctance values. Right. Now our aim is to find out this total ampere turns, AT total, or total MMF. Total MMF. So how will you find out? Yes, you can find out this by yes, reducing the network, by yes, minimizing. That means this S2 and S3 are parallel, so you can replace this S2 and S3 by a single reluctance. Okay, single reluctance, and then the circuit will become looks like this. Yes, it will looks like this. Yes, this is AT total. Then you have S air and S here, and the S2 parallel with the S3 combination, that is effective reluctance. Then you, yes, then we have this 5. Okay, yes. Then 80 total will be 80 total will be equal to 5 into S plus SAR plus S2 parallel with S3. So 80 total you will get some value. Then 80 total equal to N into I. So I, that is magnetic current, will be equal to 80 total divided by N. So you will get the answer. So that is the whole procedure. Okay. Or you can solve this problem like in terms of H and L also. H and L actually in this textbook they solved in that method. First they have calculated the, for air gap they have calculated the flux density, that is phi by A. Phi it is given, right? A is also given. So phi by A, that is Bg, flux density they have calculated for air gap. And this Bg divided by mu 0, mu r, you will get Hg, that is magnetic field intensity. So Hg into that air gap length, you will get the mmf drop. In that mmf drop or 80 ampere turns drop across that air gap. That is that means your this, yes, phi into SIR, phi into SIR. This you will get directly. Okay. Then the next in the next step they have calculated for, actually the flux density again they have to calculate for path L1. That means B1 we have 0.16 Tesla. Okay, the same flux density we have, because phi by A, phi is same, area, cross sectional area for the central limb is same as that of air gap. So then H1 will be different. Why? Because we have, in this case we have mu 0 mu r, where mu r is 800. Okay, and then if you calculate H1, then H1 into the length L1 minus 2. Okay, L1 minus 2 you will get, sorry, minus 2 means minus 2 mm. Okay, minus 2 mm you will get the mmf. That means here what we have calculated is 5 into S. 5 into S. You will get it directly. Okay. And then this they have calculated for the path, for the two paths L2 and L3. Similarly they have calculated, but the thing is, since this S2 and S3, these reluctances are parallel, the mmf drop across these two reluctances will be same, that is 82, 83. That means 82 will be equal to 83. So you can take this one loop only. Okay, so it will be 80 total will be equal to 80 that is this is 81, this is 82, so it will be equal to 81 plus 82 plus 83. Okay, in this manner you can calculate 80 total. So that is what in this textbook they have calculated. So that means H2 they have calculated. So H2 will be equal to H3, and the length H2 into L2. Okay, for H that will be equal to H3 into L3. Both will be equal, and then finally they will add this Fg, F1 and F2, and then finally they have divided with the number of turns, capital N. Yes. So that is our two magnetic circuit problems: series magnetic circuit and parallel magnetic circuit problem solving. Thanks.